Hi, everybody. It's Professor Mitchell. Today we're starting Chapter 3 on Numeration Systems and Whole Number Operations. So in the first section, 3.1, we're going to talk about numeration systems. You will be able to understand and explain numbers, their origin, and their representation in numerals and models, different numeration systems, including the Hindu-Arabic system, and place value and counting in base 10 and other bases. Numerals are written symbols to represent cardinal numbers. So, of course, you're very familiar with the set of numerals on the bottom. These are the ones that we use. Throughout history, there have been other numeration systems that have been used. For example, you've probably seen Roman numerals before. They're still used for certain things, but the other ones are probably not as familiar to you. So through this chapter, we're going to be looking at some of these, and believe it or not, it'll really help you understand our system a little better. A numeration system is a collection of properties and symbols agreed upon to represent numbers systematically. So here's a system that I use, and you probably use it. If I'm trying to count something, for example, how many times did a certain thing come up in a list, I will use tally marks, like you see here, uses single strokes to represent each object that is counted. And to make them easier to count, we traditionally, lump them together in groups of 5. All right, so here's an example of 13 written with a tally system. The Egyptian numeration system used these things that really look like hieroglyphics to represent different numbers. The number 1 was represented by a vertical staff that looks like our number 1. And then 10 was represented using what's called a heel bone. And then other powers of 10 were represented using a scroll, a lotus flower, a pointing finger, a pollywog or burbot, and finally, astonished man. Okay, so we might be looking at that system a little bit more later in this chapter. Next, we have the Babylonian numeration system. It only used 2 different numerals to represent 1 and 10. The Mayan numeration system was kind of what we call a base 5 system. Notice that the Mayans had a numeral for 0, and that's something that a lot of other, earlier civilizations didn't have. And they also had symbols for 1 and 5. The Roman numeration system, again, this is probably kind of familiar to you, used different letters to represent different numbers. The Roman numeration system is also an example of what's called a positional system. So for example, to write the number 6, you write VI, but to write the number 4, you write IV. So there was an understanding that writing the I before the V represented subtraction. All right, and here you see more examples of the positional usage, putting a smaller number before a bigger number to represent subtraction. And that brings us to our numeration system, which is called the Hindu-Arabic numeration system. All numerals are constructed from 10 digits, 0 through 9. Place value is based on powers of 10, which is the number base of the system. So of course, for example, the numbers 163 and 361 use the same numerals, but they represent different numbers because the positions of the numbers are important. Okay, not all numeration systems had that. All right, more about place value. Place value assigns a value to a digit depending on its placement in a numeral. So in the base 10 system, the rightmost digit represents ones or units. The second to the right digit represents tens, and the next digit to the left represents hundreds. Notice hundreds, 100 is 10 to the second power. And the digit to the left of that represents thousands. 1,000 is 10 to the third power. And here you see the expanded form of the number 6,789. It takes each digit and multiplies it by its place value. Here again is the definition of exponent. If a is any number and n is any natural number, then a to the power n means a times a times a, et cetera, n times. There are n factors of a. And then anything to the power 0 is 1, except 0 to the power 0 is undefined. All right, exponents are important when you're doing place value. So one tool that's used to help children understand the base 10 system is called base 10 blocks. So you have units to represent ones. You have longs to represent tens. You have flats to represent hundreds. And then you have blocks to represent thousands. So in this example, we're going to trade 11 flats, 17 longs, and 16 units to obtain the fewest blocks possible. This is an exercise that you can do to help children understand the concepts of carrying and addition and borrowing and subtraction. So I start with 11 flats, 17 longs, and 16 units. And what I'm going to do first is I'm going to take away 10 of these units and trade them for 1 long. So see here what happens is 16 units becomes 1 long and 6 units. All right, 16 units is equal to 1 long and 6 units. So after the first trade, we have 11 flats, 18 longs, and 6 units. So that's fewer blocks than we had to start with, but we can do better than that. Now we can take some of these longs and trade them in for a flat. So we take our 11 flats, 18 longs, and 6 units. We're going to take 10 of the longs and trade them in for 1 flat. So 18 longs becomes 1 flat and 8 longs. That leaves us with 12 flats, 8 longs, and 6 units. So that's even better. But we can take it one step further because remember, we also have blocks. So finally, we're going to take our 12 flats. We're going to trade 10 of those flats for a block. And that leaves us with 1 block, 2 flats, 8 longs, and 6 units. And that's the best we can do. That is actually a representation of the number 1,286. Okay, so the fewest possible number of blocks that you can use to represent this number is 17 blocks. I should say pieces. All right, fewest number of pieces. Yeah, block means something specific. All right, now it is thought that the reason we use a base 10 system is because we have 10 fingers, all right? But it's worth looking at other base systems, other number base systems. For example, base 5, which is called quinary, is based on the concept of just doing all your counting on one hand. It only uses the numerals 0 through 4. And then when you get up to what we typically think of as 5, think of that as 1 hand and 0 fingers, and that number is written as 1, 0. All right, so with the units and longs system, think of this as 1 long and 0 units. But this time a long only has 5 units in it. All right, and continuing, be careful not to read these numbers as 10, 11, 12, 13, because that kind of suggests base 10. So I always read numbers in other bases just as 1, 0, 1, 1, 1, 2, 1, 3, 1, 4. Notice 1, 4 is 1 hand and 4 fingers. And then the next number would be 1 hand and 5 fingers. But remember, there is no numeral 5 in base 5. So that would be 2 hands and 0 fingers. And that would be written as 2, 0. Another fun way to represent base 5 is with pennies, nickels, and quarters. You can represent base 10 using pennies, dimes, and dollars, dollar bills. I like to use pennies, nickels, and quarters to represent base 5. So hopefully in a future section, I'll have the opportunity to show that to you. All right, so in this example, we're going to convert 11244, base 5, into base 10. So this turns out to be pretty simple, as long as you understand base 5. In the base 5 system, instead of having ones, tens, hundreds, thousands, etc., you have ones, fives, 25s, 125s, and 625s. Notice that those are all powers of 5. So you set up this table. Our number here has 5 numerals in it. I'm not going to call them digits because that's also a kind of a base 10 concept. Fill those in underneath and then write it in expanded form. So this number 11244 in base 5 represents the number 1 times 5 to the 4th plus 1 times 5 to the 3rd plus 2 times 5 squared plus 4 times 5 to the 1st plus 4 times 1, which comes out to 824 in base 10. All right, now you can make, you can use any base you want, really. Another common one is base 2. That's called binary. There are only 2 digits, 0 and 1. And this is what computers use because the 0 and the 1 represent 0 sort of represents that a switch is off, and 1 represents that the switch is on. All right. Okay, so very similar to the last example, if we wanted to convert 10111 to base 10, remember now we are in base 2, so our place values are 1, 2, 4, 8, 16, which are powers of 2. And when I put my numerals underneath those place values, I get 1 times 2 to the 4th plus 0 times 2 to the 3rd plus 1 times 2 to the 4th plus 1 times 2 to the 1st plus 1, which comes out to 23. Now you can also go the other way. I'm sorry that popped up right away. If I wanted to convert the number 27, which is base 10, our ordinary, familiar 27, into base 2, that is a little more complicated, and I thought that I would show you this on my tablet. I thought it might be easier to follow than what you see here. What you see here is basically long division, but it's written in kind of an unfamiliar way. So I'm going to switch over to the tablet and show it to you the way that I would normally do it. Okay, so let's see, where is my screen? Okay, so we're trying to convert the number 27 to base 2. So the first thing I'm going to do is set up my base 2 system. And maybe I don't know right ahead of time how many numerals it's going to take to write this number in base 2. So I will start over here with a 1, and then 2, which is 2 to the 1st, and then 4, which is 2 to the 2nd, and then 8, 16. And I'm going to stop there because if I go to 32, 32 is bigger than 27. So I know that to represent the number 27, I'm not going to need any place values 32 or bigger. So the first thing I need to know is how many 16s are there in 27? And so that's just a long division problem. 16 into 27 goes 1 time and leaves 11. So this 1 is going to go here. And now I need to ask how many times does 8, the next place value, go into 11? It goes 1 time. So that 1 is going to go here. The next question would be how many times does 4 go into 3? And the answer is 0. Next place value is 2. 2 goes into 3 1 time. And then 1 goes into 1 1 time. Okay. So that means that to represent the number 27 in base 2, you would write it as 1 1 0 1 1. And don't forget to put the subscript that indicates what base you're in. If I don't see a subscript, I assume it's base 10. All right. So that's what they're doing here. They're doing long division. I thought it looked a little confusing, especially if you've never seen it written that way. All right. Another common system is base 12 called the duodecimal system. That uses 12 digits. So we have to create some new digits that we don't use in our system. So we will use T and E to represent 10 and 11. Base 12, you have 12. Oh, they do call them digits. Okay. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 2 new digits, T and E. So that takes a little getting used to. All right, converting a base 12 number into base 10 is easy. Just remember that your base 12 place values are 1, 12 to the first, and 12 to the second. It might be helpful, actually, if I switch back to the tablet. They did not show quite as much work on this one. Okay, now let's see. It was E2T, wasn't it? Yes, it was. Okay. All right. So E2T in base 12. My base 12 system has 1s, 12s, and 144s. So whenever you have the digits E or T, it might be helpful to write, a traditional 10 or 11 next to it. Okay, and so this is how they came up with 11 times 10 to the, or 12 to the second, plus 2 times 12 to the first, plus 10 times 1. Okay, and I can't do that math in my head, so let's switch back to this. Okay, so that comes out to 1,618. Okay, let's see. Okay, the next example is to convert 1,277, which is a base 10 number, into base 12. So this is the long division thing that we did earlier with base 2. I am going to switch back to the tablet. All right, so in base 12, you have 1s, 12s, 144s, and 12 to the third. I believe 12 to the third is bigger than 1,277. I'm 99% sure it is. Let me just double check. Yes, 12 to the third is 1,728. So we're not going to need any of those. The first place value we're going to need is 12 to the second, which is 144. So the first thing I want to know is how many times does 144 go into 1,277? The answer is 8. And let's see, 8 times 144, that would be a 2, carry the 3, 5, carry another 3, that would be 1,152. And then the remainder is going to be the next number that I divide 12 into. So I do need that remainder. That remainder is 125. So I know I'm going to put an 8 under here. Next, I need to know how many times does 12 go into 125. It goes 10 times. Okay, but remember that's not how we write the number 10 in base 12. We write it like this. And we have 5 left over. So instead of asking how many times does 1 go into 5, you can just put a 5 there. So that means in base 12, the number 1,277 is written as 8T5. All right. Oops. Okay, so they write it like that. Okay, and for the last example, Rob used base 12 to write the following, the number G36. So please don't panic. G is not another digit in base 12 that I didn't tell you about. It represents a mystery unknown digit that we're going to figure out, okay? So the number G36 in base 12 is equal to the number 1,050. All right, and that is enough information to determine the value of G. So if you just write this mystery number G36 in expanded form, it would look like this: G times 12 to the second plus 3 times 12 to the first plus 6 times 1 has to equal 1,050. So now this is just a little easy algebra problem. 144G plus 36 plus 6 is equal to 1,050. You combine these like terms, gives you 42. Subtract 42 from both sides, you get 144G equals 1,008, which means G must be 7. So the number 1,050 in base 10 is equal to the number 736 in base 12. For section 3, we'll see you next time.